So in this video we are going to discuss the axiom of choice, and we're going to give an example of where it's used. Indeed, we're going to construct the Vitali set, and we're going to use it as an example of where the Bayes measure breaks down. So it's an example. If you believe in the axiom of choice, it's an example of a subset of the real numbers, indeed the subset of the closed interval 0, 1, which is the Bayes measurable. Okay, so the axiom of choice then, the axiom of choice. The axiom of choice The axiom of choice states that if you have a collection of non-empty sets, so let's say, oh dear, the light isn't quite bright. It makes it difficult to see. Can we see that now? I think so, yes, that's better. If you have a collection of non-empty sets, so let's index it. So A alpha, where alpha is an arbitrary index. Alpha indexes the sets. So we have set that indexes the sets. So allow me to have countably many sets now, to have a countable number of sets for a moment. Number of sets. So I shouldn't really be writing this because this isn't part of the axiom of choice, but allow me to have countably many sets, then we could index it A1, A2, A3, all the way up to AN. So if it's finite, it would stop at AN. Obviously, if it's countably infinite, it would go on and on and on, and we could have it in bijection with the natural numbers. So these are all sets. So they're all non-empty, so they contain something. Then the axiom of choice applies to any collection of sets. This doesn't need to be countable, so it can be uncountable, which is why I've used the index alpha, which suggests that the index may be uncountable. So we could be indexing this by the real numbers, or we could be indexing it by the power set of the real numbers. It's just each set is in bijection with some indexing set, so we could be using an arbitrary indexing set. Okay, so each of the sets is non-empty. Each of these sets is non-empty. Then the axiom of choice states. The axiom of choice is that I can go along. I can pick an element, a single element of each set. And stick them together and put them all into one new set. So it's an axiom that allows you to create a new set. And you may think, well, that's pretty obvious. It's obvious in the finite case. The axiom of choice, because I can write out the sets and I can pick an element from each set and put them together into a new set and create a new set. It's not so trivially obvious when the index set is arbitrary that you can do that, because obviously you can't do that. No computer can actually construct a set like this because it will never actually ever do it. So if you believe in this axiom, which, it's pretty believable, you can sort of imagine the, R2 or something, and you can have each set bijecting with every single point, so you can imagine ascribing a set to every single point and somehow picking an element out of every single one. And that's the axiom of choice, that you can always do this. No matter how many of these sets you have, you can, as long as they're non-empty, you can always pick an element out of each one, bang them all together and get a new set. So it's a way of constructing a new set. Okay, so we are going to use this to construct what is known as the Vitali set, because to get a flavor of why this is so important, and it is so important. You use it all the time in linear algebra and functional analysis and things like that. Anywhere where you're having to pick bases from infinite vector spaces and things like that. Yes, you're using this axiom. So the Vitali set is a very nice basic example of how to use this. So take the set, take the closed interval 0, 1. Okay, so if we draw a picture, here is our closed bounded interval 0, 1. 0, 1. Here we are. Okay, so we have this interval 0, 1. Now, how do we construct the Vitali set? Well, we define an equivalence relation. So I want to split this up into equivalence classes, basically, and then I want to pick out of each equivalence class a single element, and I want the equivalence classes to be disjoint, and that's where I'm suddenly going to use this axiom of choice. Okay, so we define an equivalence relation by x is related to y if x minus y is an element of the rational numbers. So for instance, a half is related to a third, because if you subtract them you get a sixth. So all the rational numbers, in fact, here are related to one another. So all the rational numbers form an equivalence class, but if we take something like the square root of 2 minus 1, which will be somewhere around there, square root of 2 is 1.4 something, I think 1.41, so subtract 1 off that, you'll get 0.41, and if you add all the rationals such that you end up in this interval, that will form an equivalence class. If you take pi and you subtract off 3, that will come down somewhere here, and then you add every possible rational such that you still remain in this interval, that will form an equivalence class. So that's what we're doing here. So we want to show that this is, firstly, we need to show this is an equivalence class. This is an equivalence class, and the three properties you need, equivalence relation rather, is it needs to be reflexive, meaning that if x is related to x, so that's pretty obvious because x minus x is 0, which is a rational number, so tick. Symmetric, so if x is related to y, so if x is in an equivalence class with y, it needs to imply that y is in an equivalence class with x. X minus y is an element of the rationals, implies that y minus x is an element of the rationals, tick. That implies that y is related to x. So finally, transitivity. If x is related to y and y is related to z, well, this one gives us that x minus y is an element of the rationals, and this one gives us that y minus z is an element of the rationals. So if I look at x minus z, I can rewrite this as x minus y minus y minus z. No, that's not right. Plus y minus z. So these are both elements of the rational numbers. So I'm adding two rational numbers here. So I get another rational numbers. Therefore, this is a rational number, and therefore x is related to y. So it therefore does partition the set successfully. It partitions it up into these equivalence classes, and that's where these three axioms come from. What we're trying to do is make sure that this relation we've defined is actually splitting up our set into a well-defined equivalence class where each of these sets is disjoint from all other ones. Okay, so we now use the axiom of choice to construct the Vitali set. We now use the axiom of choice to construct the Vitali set. Construct the Vitali set. Okay, so pick an element x. Let's say, what can I call it? An element x. So let's call, okay, so let me just put another thing up here. Let's call the equivalence classes, E sub, let's say E sub alpha. So equivalent class and alpha is just some indexing set. So each of the equivalence classes basically. So for instance, the rationals forms an equivalence class. We don't know what this indexing set is, but it's indexing the set of equivalence classes. So what we have now is this set of sets, this huge collection of sets indexed by some indexing set, and we're using the axiom of choice to say I can pick an element from each one of these sets and stick it into a new set. So pick an element x sub alpha from each e sub alpha and stick it into a new set, a new set. This set is called the Vitali set. This set is called the Vitali set. And is usually given the symbol V. The symbol V. So, okay, so that's the construction of the Vitali set. And now what we're going to do is show that the Vitali set is non-Lebesgue measurable. Okay, so if you don't know measure theory, if you have no idea what the Lebesgue measure is, then maybe now is the point to turn the video off. You've seen the axiom of choice, you've seen how it's used to construct some fancy set. Okay, we're going on now. Lebesgue measure. So, right, so what we're now going to do is we're going to do something a little bit unmotivated at first, but you're going to see the motivation as we go on. So what I'm going to do is we are going to translate this set basically. So I want to translate the set V by a rational number within -1 to 1. Okay, so it's still looking a bit difficult to see. Can you see that? Yes, I hope so. We want to translate the Vitali set. Okay, so what's the motivation for this? If we translate the Vitali set, so let me just draw you a picture of the Vitali set. So we have this interval 0, 1, and some points in here will be elements of the Vitali set. So if we've let 0 be an element here, obviously the Vitali set isn't a single defined thing. You can let it be because the choice was arbitrary in essence. You can choose whichever element of each equivalence class you want, but it's one of those. Okay, so we've chosen some elements, and they might look like that. So obviously 0 and 1 are not going to be in it. We've chosen 0 as our one rational number to be in it, so 1 isn't going to be in it. And none of the other rationals are going to be in it. So all of these other points are non-rationals. Okay, so this is the Vitali set. Okay, so we want to show that it's not Lebesgue measurable. We want to show it cannot possibly be Lebesgue measurable. Lebesgue measurable. And by that I really mean, what I really mean is take the length function defined on the set of intervals, or if you want, the algebra of subsets generated by the set of intervals, and extend it to a outer measure on the power set of the real numbers, and basically this set is not going to be measurable, lambda star measurable. It's not going to be measurable with respect to the outer Lebesgue measure. And that's what I want to prove. And the way we're going to do that is we will assume it is Lebesgue measurable. Assume it is Lebesgue measurable, and we will come up with a contradiction. So we assume that the Vitali set is Lebesgue measurable. Okay, so what next then? So we're going to continue with this thing, and basically the Lebesgue measure, the outer measure is translation invariant. I can move this entire set up this way, I can move it down this way. The measure of it is still the same with respect to the Lebesgue outer measure. Therefore, I will translate it by these things. So I will want to construct translated versions of this set. Translated versions of this set. Which we will call V plus Rn, where Rn is an element of -1 to 1. And I should have explained, because -1 to 1 contains countably many rationals, I can list them. I can put them in bijection with the natural numbers, so I can index them with the natural numbers. R1, R2, R3, R4. So you take rationals, you index them with the natural numbers, they are all within here, and they go on and on and on and on. Obviously this is not them in their order, you cannot list them in their order, but we can list them because they are countable. Okay, so here we go, we construct these new Vitali sets, which have been translated by some rational number within -1 to 1. So, what is this set now going to be within? What we're now going to do firstly is we're going to union now over n is equal to 1 to infinity, all of these sets together. And basically I want to look at this thing because this is very, very important. Firstly, what I want to convince you, I want to firstly convince you that this is a disjoint union. Firstly convince you that this is a disjoint union, that this is a disjoint union, i.e. the intersection of Vrn with V plus Rm, where m and n are not the same, is equal to the empty set. So n is not equal to m. So how would I prove that? Well, we'll prove it by contradiction. Suppose x is an element of both. So x is an element of V plus Rn, and x is an element of V plus Rm. Then, since it's an element of this, it must have some x alpha, where x alpha was an element of the initial one of the equivalence classes, and then plus this rational Rn. So it must be one of the elements of the Vitali set plus Rn, and equivalently in here it must be some x beta plus Rn. Okay, so if these two were equal to one another, i.e. they were in the same set, they were in both sets, then they would have to be equal to one another. Therefore, x alpha minus x beta would be Rm minus Rn would be a rational number, which is a contradiction because x alpha and x beta were assumed not to be related to one another. So they were assumed not to be a rational number minus a rational number. So you might say, well, how do I know it's not? Well, it's obviously... Right, okay. Slow down and talk this through properly. The first thing is that it's obvious that x alpha and x beta are not the same, because Rn and Rm are not the same. So if you had two numbers that were exactly the same, i.e. you picked the same element of here and the same element of here and added it to these two and somehow got the same number, then you're in trouble, because these two numbers you added onto it were not the same. So x alpha and x beta cannot be the same elements. That would imply that x alpha minus x beta was equal to a rational number. That is a contradiction, because we chose one element of each equivalence class, and only one element. If x alpha minus x beta was a rational number, then they would be in the same equivalence class. So in the Vitali set, we would have two elements of the same equivalence class, which is a contradiction. Therefore, V plus Rn, this set, where I'm defining this by, sorry, I should have defined this more rigorously, V plus Rn, I mean take every element of the Vitali set and add Rn to it, so I'll just write that down. Rn is defined to be V plus Rn, where little v is an element of big V, okay? So V plus Rn intersection V plus Rm is therefore equal to the empty set. It can contain no common elements. Therefore, this union is a disjoint union, is the first thing we want to say. To 1 intersection V plus Rn. And that's going to be important because that means that when we come to do the Lebesgue measure on it, we can apply the fact that if this was a measurable set, that, you know, things would work nicely. If these were all elements of measurable sets, then this would be countably additive, basically, is what we're going to use later on. Okay, so another observation of here is that this is a subset of -1 to 2. Why is that? Because everything in the Vitali set is between 0 and 1. So if you're in V, you're between 0 and 1. Rn is an element of -1 to 1. So the most extreme thing you could happen with regards to getting small is you could have 0 minus 1. So you could go down to -1 over here. Similarly, if you were, the most extreme way you could go up here is you could have 1 and you could add 1. So it could go up to 2. Therefore, this is contained within the interval -1 to 2. The next claim, up we go. Next claim is that the interval 0, 1 is actually contained within this union, n is equal to 1 to infinity of V plus Rn. Now, why is that? So, the Vitali, and I'm just going to pause this video here and we will continue this in the next video.